Okay, so in this video, what I hope to do is I just want to describe a demo that I'm going to try to video for you. So I'm hoping that this little setup of the demonstration will be a relatively short video, but let's see how it goes. Um, so the setup is going to be the following. What we're going to have is we're going to have a coil of wire. And so there's going to be many coils. I'm just going to draw a few of them. So it's just a wire wound into a coil. And in one of the situations that was described in the last video, what we imagined is that we attached a current meter, an ammeter, to our coil. What I'm going to do is slightly different. I'm going to attach not a current meter, but I'm going to attach what are known as LEDs, a light emitting diode. And so we're going to have one that's red. And then in parallel with that, I'm going to have one that is green. And what I'm going to do is I'm going to put them in parallel but in opposite orientations. And so this is a green LED. And so what do we need to know about LEDs? So an LED is a light emitting diode. So what a light emitting diode does, or what all diodes do, in fact there's some that don't emit light, but they pass current on only one direction. So diodes pass current in only one direction. It's like for a water pipe, it would be like a one-way valve. So how it works is if you had a diode, the diode symbol for diodes that don't emit light is this triangle with a bar, and there's these the little arrows in our LEDs, these little arrows up here indicate the light coming out. So if we don't have one that emits light, then we just omit those little arrows. So what we would do is if we had a circuit that looked something like this, where we take the positive terminal and the negative terminal of a battery, and then we have a resistor and we have a diode. In this situation, we would get a current that's not equal to zero. The diode is kind of like an arrow, and it's pointing in the direction that allows current to flow. So this orientation, this configuration results in a current. On the other hand, if we took the exact same circuit, but we just flipped the direction of the battery, so there's our resistor, here's our diode, and if we take our battery and we make this the negative and that's the positive, then the current that we would get, I, would be equal to zero. And so in this situation, the battery would try to cause a current to flow in the direction that's not allowed by the diode. Okay, so this configuration results in no current. Okay, so let's go back to our LED case and our coil, and let's suppose that we took a bar magnet, and suppose this is the north pole of our bar magnet, and so it's making a magnetic field that comes out like this. Okay, so if we took, say, the first situation where let's move our bar magnet towards our coil with some velocity, then we're going to have in our coil a magnetic field B that is increasing, and it's pointing down. So this is the same kind of situation we analyzed in the last video. And so what will happen is there will be an induced current that will oppose that change in magnetic flux, that increase of magnetic flux. So we get an induced magnetic field that acts in the direction opposite of the increasing magnetic field B. And so by the right-hand rule, our current would actually, yeah, so let's see if I got the color right. So our current B induced would require a current I induced that is in this direction. And so that is the direction that would go like this. And so we would have a red current that would flow in this direction. Okay, and so that's, I want to change the color of my diodes because it didn't work out the way I wanted. I'm going to redraw my diodes, but this time I'm going to put the red one over here, and I'm going to put it in this orientation. So there's our red LED. And then I'll put my green one over here. Okay, so if we have the magnetic field increasing in the downwards direction, B induced opposes that change, and we would get an I induced that would flow in this direction, I induced. And so that goes through the red diode, but it can't go through the green diode because it's the wrong direction. And so in this case, our red light turns on. Okay, so let's try to draw exactly the same thing. And so what we're going to have is a coil like this. Then we're going to have the north pole of a magnet like this. And this time what we'll do is we'll move our magnet, we'll pull it away from our coil. And so my red LED, okay, is going to be pointing in the upwards direction. Let's put the red LED in. So I think I want the red LED in this direction, and then I want a green LED in the opposite direction. Red LED. Okay, so now what we would have is, let's see if I can be consistent with the color. So purple. We're going to have a magnetic field that points down because we're next to the north pole of the magnet. But because we're going to pull the magnet away, the strength of that field will be decreasing. Okay, so that means we're going to get a induced magnetic field that opposes that change in magnetic flux. So it tries to sustain what was there. And by the right-hand rule, we would get an induced current that would be going in this direction, I induced. It can't go through the red LED because now that's the wrong orientation. And so it can go, however, through the green LED, I induced in that direction, and we get the green light turns on. Okay, so that's the first demonstration that I'm going to try to show you. I'm going to try to show you that depending on whether the magnet is going towards or away from our coil will determine which of the LEDs turns on. And so it's a demonstration of both the Faraday effect, or Faraday's law, where a changing flux results in induced current, and Lenz's law, which determines the direction of that induced current. The induced current creates an induced magnetic field that tries to sustain the magnetic flux that was in place before the change occurred. Okay, I'm going to try to do part 2 of a demo, and what we're going to do is we're going to have a long conducting tube. So we're going to have a long conducting tube. So this is a conducting hollow tube. It's going to be made of copper. And what we're going to do is we're going to take a magnet and we're going to drop that magnet inside the tube. So it's going to be a strong magnet and it's going to be falling down. So let's do it this way. Let's say that the magnet is going to be falling this way. And let's suppose that here we have the north pole of the magnet and here we have the south pole of the magnet. So that means we have a magnetic field that is at the north pole pointing down, and at the south pole, well, it's also pointing down. So that's the magnetic field. Okay. Draw my magnetic field lines a bit nicer. So what I want to think about is a section of our copper tube that looks like this. It's a little conducting ring, and we have one that is below our magnet, and so we're going to have a magnetic flux increasing through our conducting ring. If the magnetic flux through that conducting ring is increasing, then what we get is a B induced that opposes that change. And how does it oppose that change? It creates a current, I induced, by the right-hand rule that flows in the direction that has been indicated there. And so now we have a current ring, but we know that a current ring acts like a little bar magnet. And so it's like we've got a north pole and a south pole of a little bar magnet as a result from our current ring. And so now we have a north pole of our current ring due to our current ring facing the north pole of our falling magnet. And so those two oppose each other. And so this ring of current is going to oppose the motion of the magnet, which is falling down due to gravity. Okay, and then we could do something similar above. So over here, we've got another little conducting ring, but this time our magnet is falling away from that conducting ring, and so the magnetic flux is decreasing through this top conducting ring. Okay, so the induced magnetic field would tend to oppose that change in magnetic flux, and so it's going to be in the direction of the blue magnetic field lines B. So to make a induced magnetic field in that direction, we would need a induced current in our little conducting ring that flows in the direction shown. So it's in the front face of the tube, it points from right to left. So notice that the induced magnetic fields above and below are in the opposite directions, and the induced currents are also flowing in the opposite directions. So we have now a current loop in this top conducting ring that is like a bar magnet, but now the north and south poles are flipped compared to what it was in the bottom conducting ring. And so there's an attraction between the north pole due to the current ring and the south pole of the falling magnet. And so both current loops create induced magnetic fields that oppose the falling magnet. And the result is the magnet falls slower than you might naively expected. So if we didn't think there was any kind of magnetic effect due to the copper tube, we might expect it to fall just like free fall. Copper, after all, is not magnetic, so it's not any magnetism associated with the copper at all. It's just the fact that the copper tube is a good conductor. Okay, and so what we'll try to do is we'll try to make a video to demonstrate both of these effects with the LEDs and with the copper tube. All right, thanks.